of us. I did not really know him for too long. It wasn't really until the beginning of the semester when he told me, hey, I had to do some Capstone before graduating from SSU. So I asked him, what do you like to do? And he told me he actually double majored in both physics and geology. So I said, oh, well, why don't we try something to test your physics skills and apply this physics skills knowledge to geology, so mineral samples. So here he's going to show you how he worked on a system to use physics to eventually tackle these mineral samples. Thank you.
My name is Felix, and this is my Capstone design project. Like Dr. G was saying, this was a continuation of a geology project where it was mostly finding minerals, rocks, and trying to find some fractured offsets. But with physics, I wanted to find out a little bit more about how this cathode-luminescent could work and how we can improve on it. So here you see, this is a brecciated mudstone. You can see it's fairly bright orange and yellow. That's because it's rich in calcite. So what I wanted to do with my cathode-luminescence, I wanted to put some spectroscopy on it because I wanted to be able to analyze the light that came off of my rock samples. So that was my objective. So I wanted to combine cathode-luminescence with spectroscopy, and I just wanted to identify the light. So CL works by emitting a high voltage beam of electrons onto the sample. It excites the sample into a small area here, and you get many different kinds of light that shoots off. I'm mostly into the UV and cathode-luminescence. Some X-rays do come out, but it's protected by a glass lead plate. And later on, I'm going to tell you about SEM EDX that actually produces these same electron and chemical signatures. That it's the same concept, really. It's a high beam of electrons that excites a mineral. But cathode-luminescence just reads UV light. So the way it works is a beam of electron pushes electron to a higher stage of higher energy level, and when it goes back down to its ground state, it emits some light, and I get a graph of the wavelength of this spectroscopy that I want. Here's my CL instrument. So originally what I did is I had this cathode-luminescent beam right here, and vacuum chambered all to itself, and it was really hard to get any kind of reading on it. So what I did is I modified it to an old petrographic microscope, and I was able to also get some funding from the college and get a high definition camera and mount it to the top. And so that way I could load it into a computer and get these images. And this is the control panel. The beam works at levels of, let me show you, the beam works at levels between 1 kilovolt to about 30 kilovolts, but I've never gone to 30 kilovolts. I usually go around 20, and it works under vacuum between 20 and 10 millitorrs, so very low vacuum. And I can adjust the focus of the beam in amps. So just to tell you how my samples are set, this is the vacuum chamber here, and when I put a sample, a thin section or a small piece of rock, the beam direction goes this way. And I have magnets on top that redirect the beam on top of the sample. And of course, with the microscope, I'm able to take pictures of it. And once again, this is a vacuum chamber here. So it's a very small vacuum chamber. I can put about half of this pack of cards into my vacuum chamber for a sample. So then I was able to attach my UV spectrometer on it. It was a spectrometer that the physics department had already. It's an Ocean Optics UV S200 spectrometer. We can read the range of wavelengths from 350 to 1,000 nanometers with a resolution of 1 nanometer. And this just operates at room temperature because the cathode-luminescence doesn't heat up my samples, doesn't damage them whatsoever. And so when I attached the cable onto one of the eyepieces, it made it so I could really zero in on my sample. And the picture I get from my camera is actually the wavelength I'm getting from that picture. So what I wanted to do is with these pictures and the wavelengths that I was able to get from my samples, is I wanted to correlate them with the chemical composition of the samples. So we used the SEM EDX at the Tech Laboratory here on campus. And the EDX is very similar to the cathode-luminescence, except it reads the characterized X-rays and is able to tell you what the chemical composition is. But basically, it's the same concept. We're shooting a high beam of electrons onto a sample, and it excites the electrons into a lower state and emits X-rays. So this is one of the mudstones that I had. This is in plain light. This is just a picture of a microscope, about 40 times magnification. And this is the bright shaded mudstone that's off the Point Arena, which is close to the San Andreas Fault. And this was originally just to show the offset. And when you put it in CL, it glows red. And you see all the calcite is red. The rock itself is there's a lot of calcite, a lot of impurities. So what I did is I was able to get this wavelength. It's a pretty good wavelength with it. And I want to know what this correlates to through the SEM. So I took it through the SEM. This is a scanning electron microscope. It's up close. You can see the difference. You can't really tell anything from this picture compared to on the CL where you see some structure of the vein. So it's kind of nice to have a CL do that. But it's really good at telling me the chemical composition, so you can see that this mudstone is full of different kinds of elements like calcium, magnesium, silicon, just a big mess of different stuff. That's why it's called a mudstone. And here's chemical composition again, percentage, so lots of different stuff. So what I wanted, so this right here doesn't really tell me too much about what chemical composition is, so I wanted to find a pure sample that would give me just a couple elements in there that I could tell that's what the wavelength meant. So I decided to get some quartz that I was lucky to get from the geology department that was washed with hydrochloric acid, so it was fairly pure. And what pure is, again, plain light at 40 mag. And to get this to glow in CL is really difficult because it's like a piece of glass. So this is the light emission I was able to get. CL is light green, really hard to pick up intensity. So this is the quartz grain I was able to get. Once again, this is the wavelength down here, and this is the intensity that counts how many photons I was able to capture. The good news with this is, even though this graph could be a little bit cleaner, it's right to where someone was working with CL in a published paper, and they were able to find some very similar wavelengths at 546. So that was really nice to hear that the CL that we put together seemed to be working properly. When we put in the SEM, here's a picture of the quartz grain. It's really pretty, but really doesn't tell you too much. This is the chemical composition, which is nice. So this quartz grain only has oxygen silicon, which is nice because that wavelength back there will tell you that that's mainly the composition. Again, here's the quartz grain, atomic percentage. So it's fairly pure. Does have some imperfections, I'm sure. So the CL seems to be working fine. It's collecting good data. It's capturing wavelengths, even at certain minerals. I ran out of time. I need to collect more samples, and what I want to do is catalog a bunch of samples with different wavelengths that correlate to the chemical composition, so that we know next time we put a sample in, we'll know what the wavelength is and what it does. But then the next step would be why these wavelengths are what they are. You got a pure quartz crystal, or supposedly pure. Why does it emit that certain wavelength? Is it fractures? So that would be my next step. And I would really like to thank the Sonoma Physics Department for helping me continue this work for the Geology Department. My advisor, Dr. Shee, the Physics Department, and Dr. Matty Mukherjee, who started me on this project in the Geology Department. And of course, I wouldn't have been able to do any of this work without the techs of both the Physics and Geology Department, John Collins and Steve Anderson. So thank you very much.
I have a question. So this seems like a really neat pairing. I think the pairing is because of you, not because there's an existing way that the geology and the physics department have been talking about this, right? You brought in a piece of equipment and say, let's bring some physics acumen into making this new measurement. What would you say is a way that this work could continue forward? Is it you just have to find another student like this, or
I've actually talked to Dr. Shi about it and Dr. Matty Mukherjee, and they both seem to be willing, if there's a student that wants to continue this work, I think there's applications in both. And personally, I mean, for me, I feel kind of selfish because this was such a great tool as far as educational. I got to play with optics, electronics, I got to play with a vacuum chamber, I got to make samples, prepare samples, and learn the physics and the geology of everything. So this has been a great experience for me, and I'd love for someone to continue it. It'd be great if it was maybe even a parent of a geology student and a physics student. Is that it?